Yes, teacher.
Okay, so I'm going to show you some projects having been done in DC-Lab. So right now we have a mobile robot development for robot contests and also for research. And for mechanism and manipulator, we don't have so many projects and for the robot arm itself, but we have project on serial and parallel mechanism solar tracker. And the serial axis solar tracker means we use two rotary motor, to rotate 2 degrees of freedom. Then we can have tracking, can have object tracking. So for those who are new to DC-Lab, you can interrupt me and ask for clarification. And you can ask either in Khmer or English. For parallel mechanism means mechanism that use rigid body on linear actuator or something in order to move the mechanism. And we have project for the unmanned aerial vehicle, such as multi-rotor like quadcopter, and people usually call it drone. And also we have projects to develop a fixed-wing unmanned aerial vehicle. It's like a small aircraft or small airplane with a fixed wing that need runway in order to take off and landing. And we have project on artificial intelligence, specifically deep learning, that focus on object detection. Yeah. So for this project, we intend to use camera to capture video and then use deep learning algorithm to detect objects in the camera and then can command or control actuator to do some tasks with the tracking. And the last one is about spacecraft development. So we have project to develop rocket and a small rocket and a small satellite. Yeah, for the rocket, we are currently using solid fuel that can be made using sugar and KNO3 fertilizer. So we expect to launch it to reach around 200 to 400 meters. So actually our first launch couldn't reach that high. It only reached around 30 meters. So we need to improve more on the engine and many other subsystems. For a satellite, we want to develop a laboratory grade satellite that have all the function like a satellite that can capture image to a specific location on Earth that it command under the command from user on the ground. Okay, so anyway, we just want to have satellite that can be experimented on the Earth first. We do not have a plan to launch it yet. It depends on budget that we can have. If we can get more budget, then we can consider launching we consider building a space-grade satellite and launching. For now, just focus on experimental satellite, which can be operated in the lab. So for my robot, you can see here a development of a three omni-wheel robot that we try to have a specific in. So let's say it was successfully implemented. Okay, I mean the development was successfully done. So we are looking at developing board that can navigate on its own. So it's called open. So for mobile robot, actually, in terms of research, we have completed several objectives. For example, the investigation of the performance investigation for IMU and encoder sensor fusion, and we have conducted an experiment already. And for the objective number 2, we investigate the performance of sensor fusion between IMU, encoder, and liner. But we have done it with simulation only. So yeah, I need to explain more what IMU means. So it's called inertial measurement unit. Okay. Oops. Wow. So okay, so IMU mean inertial measurement unit. So in here it has accelerometer, measure acceleration. Okay. And it has gyroscope, measure angular velocity. So in the case of mobile robot operating on a plane XY, we only need the yaw angle that tells us how much the robot rotates with respect to the X angle, X axis. Okay, so how much? So this one is same as the axis. We need gyroscope to measure the angular velocity for this rotation, like this. So, but actually gyroscope can be used to measure angular velocity in the space. So we have object that rotate in the space. So it can give us the component of angular velocity in the space with 3 components like that. Okay, H, Y, Z. So this is the meaning of gyroscope. And IMU, some IMU also have magnetometer. Yeah, magnetometer that measure the direction of magnetic field. So if it is used in space, it can also measure the direction of magnetic field B that has 3 components as well. Okay. So magnetometer is important to measure the absolute angle of a robot with respect to the north axis. Okay. So for example, H is point the H global is point to the north. Yeah, Y can be east, for example. If this is Y, and then Z should be yeah, Z should be like this. Yeah, but anyway, for mobile robot application, magnetometer is used to measure how much the robot rotate from the x-axis. Okay, how much the angle it rotate from the x-axis global or the north. Yes. Actually, both gyroscope and magnetometer are fused together in order to get this angle. Okay, this angle. Same. I explained here before on using gyroscope, and your gyroscope is we can only measure angular velocity, and we can use kinematic to compute angle, but it is in a relative manner, relative term. But magnetometer measure the angle in the absolute term because it can give the information with respect to the north axis. That's why we need both of them. Accelerometer can measure acceleration, and we can compute acceleration to find velocity and position, but it can also use to fuse with other sensor like gyroscope, magnetometer to give a good orientation in the space. So, for example, for a satellite, how do we know satellite has orientation to the Earth or to the Tonle Sap Lake, or has orientation of a camera to a forest or to a specific location? Actually, we use this IMU and use some sensor fusion algorithm to determine altitude. We call altitude. Okay, so altitude means the orientation of an object in the space. Okay, so actually it described by rotation matrix. Yeah, so if you know rotation matrix, it means you can compute the pointing, the direction or orientation of the craft, okay, of the vehicle. Okay, so here objective 2 is to use multiple sensors, so not only IMU but also with encoder and also with LiDAR to fuse in order to localize the robot, to know where the robot is. So the algorithm will calculate based on calculate the location, the position x, y, and the angle of side of the robot. Okay. So it's called localization actually. Yeah, so I don't just say read the objective, but rather explain. Okay, discard. Explain it in this way so that you can understand a little bit, even not much, but at least you know what it is about. Objective 3, to deploy the algorithm above on the hardware, but we haven't done yet. See, not done yet. Objective 4, identify lamp parameter of a low-cost DC motor by using extended carbon filter for controller design. So actually, DC motor has physical model. Okay, it has model. But unfortunately, for low-cost one, we cannot have the information of the parameters. For example, resistance of the winding, coefficient of back EMF, or torque constant, or moment of inertia of the robot of the motor. We do not know. So we use algorithm to identify lamp parameter. So actually, the DC motor can be described as a differential equation with parameter resistor, inertia, torque constant, back EMF constant, frictions, viscous coefficient friction, okay, and Coulomb frictions. But anyway, we can simplify the model to be just omega dot equal to minus A omega plus BU. So U means voltage that you supply to the motor. Omega mean, okay, so this is motor with motor here and with terminal plus minus. And then you supply voltage U. So you give voltage, a certain voltage U. This one will rotate at a certain angular velocity. You give more voltage, the speed is faster. It's like that. And the relationship between U and omega is given by this lump equation. Equation with lump parameter, this one lump parameter. Or maybe add more terms, C sine omega. So we have three lump parameter, A, B, and C. So we have already identified the parameter. We have algorithm. Yeah, algorithm, which is extended Kalman filter to identify this parameter A, B, and C. Okay. A, B, and C. And then we design a controller based on this parameter that we already identified to control velocity or position of a motor. So if we can control velocity, can control position, we can build a mobile robot, we can build a robot arm and just control on the motor. Then we can achieve the desired task for the robot. Okay. For objective 5, we want to design adaptive control based on online estimate lamp parameter. Actually, we have tested this one, but it seems does not work. Or it may work if we at least apply on offline identification first, at least one time. Offline identification means first we use the objective 4, operate the motor by using the sine wave for the input voltage here. Just put sine wave so the motor rotate forward, back and forth, back and forth. We can get A, B. and we can get some information about its error and use those information to for the online estimation using the same algorithm but online, and the controller is designed based on the online parameter, and then it will be adaptive. If robot have heavy load, more load, the parameter A, B, C change, and based on that change parameter, the controller also change, so it adapt to the change of the controller, and we expect to have a better performance. Okay. So in my work, we have tested the online estimation. If we give the initial condition correctly, it means that both information of the parameter and the information of how much the error involved. Okay, this is a little bit too deep for young student, but for senior student who have worked on this should be able to understand. And then for objective number 6, design plug and play on both mechanical structure and control hardware for mobile robot. Yes, still for mobile robot. So because we want to test control algorithm with different kind of wheel robot. So some robot use omni wheel. For example, this one use omni wheel. You can see omni wheel. And this robot use differential drive wheel, just normal wheel. Just normal wheel. And some robot use Meganum wheel. Okay, what is Meganum wheel? Let me show you. So here is Meganum wheel. Okay, it looks like this. And so here we want to design a robot platform that has that can be plug and play on the mechanical part and electronic part. So it means we can change the wheel from normal wheel to omni wheel, or from omni wheel to mechanism wheel, from mechanism wheel to what kind of wheel? Yeah, I think I don't know what to call it, but anyways, actually the most 3 important wheel is just normal one, that just like wheel of a motorcycle or something, and omni wheel and mechanism wheel. Also, we want to plug and play with different configuration, because some robot has only 3 wheel, like this one, only 3 wheel. Yeah, only 3 wheel. And mechanism wheel usually have 4 wheel, and differential drive wheel only has 2 wheel, like this. The front wheel is just to make 3-point contact on the surface. So the front wheel does not have any influence on pneumatics or motion. Okay, so here is just one have been what, and objective 2 This is the architecture for the simulation, including sensor interpreter. Yes, so we compute to get a location of H and then integrate the location into different type of measurement. Okay, so he just simulated measurement. So integrate velocity into encoder signal or data, and then integrate into LiDAR data. We integrate into IMU data, and then we corrupt the information by noise, and then implement the algorithm in order to test whether algorithm is robust with the noise or not. And here we also have controller and control to the kinematic and dynamic of the robot. Then it will has motion. H contain H itself, Y and psi like this. Okay. Not just on the direction H, but H, Y, and psi. Any question up to this point? Virya, are you here? Samrat-chan Virya? Virya, cho nhé, Virya. Tingy, do you have any question?
Not available.
Have you learned something more from here? Something new? You'll ban class bây giờ Tình nghĩ.
Ban được khổ mà.
This one about objective number 4. Objective number 4 that to identify lamp parameter. So we use the model of only 2 parameters for this equation. Only 2 parameters A and B. So the result was okay, but not really good. Right now we use we already had experimental result of using 3 lamp parameter A, B, and C. Like this. So we got very good result actually. So the next about mechanism and manipulator. Yeah, we four-wheel, 4-leg. In terms of functionality, control, or something, we could say that we successfully implement the controller to the microcontroller. Or actually, we use a PC, not microcontroller at the time. But unfortunately, the robot was too heavy. It cannot walk on the ground. The bell cannot sustain its weight. It just slipped over here. Yeah. So we still need to develop the optimization on the design, especially mechanical, electrical integration design. So we need to choose the right microcontroller. Microcontroller, for example, on module A or B or bone, we need to choose the right motor. Yeah, the motor should be strong with should have high torque but low velocity. So and should be the type of pancake. Yeah, pancake motor is like this.
it's yeah, not long like this. This one is not good. This motor is not good for manipulation, but we need yeah, we need pancake and with the connector like this. Okay, maybe like this. With this kind of motor. And yeah, the design should be modified as well. This is not the bad design because we found that it can easily get out of range, and yeah, we do need use limit switch to define the range, but when we experiment the motion, we still need to develop proper algorithm, and we got so many trouble because of the design like this. So the design should be changed as well. For this one is very simple tracker. Anyway, it can be a static form for young student. Speed skill that they learn on how to use Arduino, how to use some electronics, like light dependent resistor or sensor. So really there are four, yeah, four light dependent resistor used as a center, like 2, 3, 4 pattern. And with a very simple control algorithm, and then need some techniques while approximation in order to implement this differential equation on the Arduino using a C++. Parallel mechanism, this one is too complicated. I won't say much about this, but anyway, the objective for this research is to develop a dynamic equation in order to describe the motion. Then objective 2 is to design controller for the mechanism. And we have 2 papers published, one presented in the ITC conference and one published in one international journal. And next, for the parallel mechanism solar tracker, we want to build a prototype which look like this. So we have a plate, and then we have a solar tracker with the 2 axes, 2 rotary axes, this one and this one. But for the design, we may use linear actuator or rotary actuator. It depends on the convenience of design and how we build it. And then use some microcontroller to control. So let's say if this platform can be rotated or can be turned 3 axes. So this joint represents a spherical joint. Spherical joint that can rotate with respect to 3 axes. So we can rotate with respect to axes, or we can rotate with respect to axes. We can rotate with respect to this axis. So this plate has all 3 degrees of freedom, and all the 3 degrees of freedom are rotation, so that the panel up there will move due to this one. But because we want the solar panel to track the sun all the time, for example, so it must orient its direction like this to the sun all the time. So whenever we move this one up and down, we want this panel still keep pointing to the sun like this. Okay. So we need to control the rotation on this joint and this joint.
Yeah, so objective 3 is to build the prototype. So we already have the mechanical part for the system, not exactly like this. We don't use the spherical joint, but instead we use a wheel platform. Okay, we use a wheel platform that can be turned around with the one axis rotation only for now. But I think it more or less can be used for some investigation, for some experiment or some study. For example, study of energy gain from the tracker. This one would be enough. Yeah, actually we need to consider energy gain and at the same time the energy spent on the actuator 1 and 2. So here we use 2 microcontroller because this one has IMU, this one also has IMU. So if we design a platform like this, and we want to have all the mathematical modeling and control, we want to measure the rotation of this, the orientation. So we want to put, or maybe bigger bone on here, bigger. So maybe we want bigger bone on this one and pitch up on this one. Okay, but because now we reduce this one from degree of freedom to just 1 degree of freedom, maybe we only need one of them, or maybe still need both. Is that clear, Chitra? I cannot hear you. Not lưỡi.
Hello. Hello.
Okay, so let's go next. What happened? What wrong with your computer, Chitra? Cả năng lượng ở bên nhà không? Là tôi vậy chết sợi rồi có mỏ lọ.
Còn vậy
Là Chitra lại nước vô cho bà hết.
vô ban tích liệt rồi
Được sáu như vậy.
cứ là lực rồi
Tại sao nhỉ? Là lưỡi. For about actually one student has done on a simulation of dynamic and control for 6 degree freedom. So, yeah, we haven't developed any prototype yet. So the progress on the robot arm is very slow compared to other prototypes. The next theme is on unmanned aerial vehicle. So the objective one for unmanned aerial vehicle is to simulate motion control using backstepping. So backstepping is very useful for equation that for the dynamic equation that the number of output more than the number of input. So for example, for a drone, the number of input for the dynamic is only 4. 4 means that the total thrust on the same direction. So each thrust from the propeller are in the same direction, so can be represented by only one parameter, one variable, or one input, thrust T. Yeah, on the body frame. Okay, on the body frame. So on the body frame, the z-axis has the thrust T, but the x-axis, y-axis is 0. So here only 1, and then the moment can happen if thrust generated by propeller are different. If this one light thrust, this one light thrust, and this one is more thrust, this one more thrust, then it has moment like this. So in the same way, it can have moment in this axis, and also it can have moment in the axis. So the moment on the drone or the multi-rotor can have 3 components, X, Y, and Z. So these 3 input plus this 1 input, there are only 4 input. 4 input to the dynamic equation. Okay, this one is not. Yes, this 4 here. This one 0, 0, only this one, and moment. Moment L, and N. And then for the output, there are 12. Sorry, 6, can be 6. Position with respect to the north, east, and down axis. And then orientation represented by Euler angle, for example, or roll picture angle. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Okay, so output is 6, input is only 4. So number of input is less than number of output. Then backstepping controller is very useful. Objective number 2. Yeah, with the solar tracker, we want to put the solar tracker on UAV. We want to use the big quadcopter at NPIC. So we collaborate with NPIC. So now we just finished building the mechanical part of the tracker, and we consider integrating the system once we have started separated system well enough. Actually, we have more actually. Not only just purchase component, but already can say half finished mechanical part, almost finished for solar panel, solar tracker. Okay, so if someone say that, do we expect that the energy gained from the solar panel, okay, energy in, will be enough. Yeah, will the energy gained by solar panel be enough to operate the energy that get out of the motor that used for the propeller? Actually, we don't expect the energy gain would be enough, but we expect that if it can find a proper landing site, it can land there and stay there to gain the energy from the solar. Then after then it can continue its mission autonomously. Yeah, anyone can ask question. You can interrupt me and ask question. Don't hesitate. So now we can go next for fixed wing UAV. We have conducted research. We conducted a research on simulation for takeoff. Yes, just a state machine to define the stage when it take off. For example, so first it run like a taxi, and then when the front wheel is above the ground, it's not touched with the ground. It start to rotate, and then it's climbing, and then it rotate back to almost zero angle. So it has stage, okay, for the takeoff. So there and here we just simulated controller that allow the aircraft to perform as we desire. And actually for fixed-wing UAV, yeah, we have already implemented one algorithm to estimate state and parameter for the orientation. But anyway, this one is just to illustrate the powerfulness of algorithm, but actually we did not apply it with the actual model of UAV, whether fixed wing or quadcopter. So it's just a matter of testing algorithm with a model that have degree of difficulty to some extent. And another objective for fixed-wing UAV is to study the controller design for the hybrid UAV, hybrid in terms of landing, takeoff and landing. So this UAV can vertically take off, okay, take off mà này họcឡើង I vertically landing, short time vertical land. And when it fly for distance, to have a large distance, it use this propeller and fly in a straight direction like this. So we design a controller by using state machine to switch from controller act as a quad act as a quad rotor to the controller act as a propeller for fixed wing UAV. like this. For artificial intelligence, at the very early study, yeah, we test the workflow, determine the workflow of deploying deep learning model to the hardware. So we use existing model, okay, but we just how to get those model onto the hardware of NVIDIA Jetson. So just find the proper workflow environment, for example, use Ubuntu and use some many other software, maybe, or also use MATLAB actually to generate the code, the deep learning code, and then deploy to NVIDIA Jetson. Yeah, same for this one, but just different algorithm. Deep learning algorithm. It's object detection. YOLO means you only look once. Yeah, only look once, then can determine the objects, recognize the object, and throw a bounding box. Throw a bounding box means no, we will be coordinate of the objects inside the box. Yeah, you only look one, so just look one, and then recognize the object type and know the central it. The central it in terms of pixels area, okay, of the bounding box. Yeah. So with respect to the pixel of the overall here, so we know the coordinate on the X pixel and also on the Y pixel. Like that, X pixel, Y pixel. Same for this and for other bounding box. One student has implemented YOLO V4 Tiny for landing site tracking. So here, existing video that has been used with the deep learning algorithm to detect the landing site. Cái này là cho đó, cái này là H đi. So you can see that the algorithm can detect the object and draw the bounding box around the object. So from this information, if we know the information of the central it on the pixel, and then we can control the actuator to point the camera to there, and also control the quadcopter or UAV itself to land at the right place. So we are one step closer to the autonomous. Yeah, this one is same thing, but just experiment on the Android. Yeah, you can see that this is camera can track. Yes, it's camera can always track the picture.
So we have more tasks to do. For example, build deep learning model for image object tracking. Object 3. Yeah, because before we only use existing model and we use transfer learning with only few data set. A few data because we only detect one object, but in the future we should detect more objects if we want to implement to some vehicle that may confront or may need to see may need to recognize other objects. For example, for self-driving car, or even for the drone that need to recognize building or something else. And then need to integrate various deep learning model and navigation for autonomous mobile robot. Yeah, well here, first we try with mobile robot because it is very safe and we can easily build a prototype. And the last point is about spacecraft. So for our rocket, we have developed the engine and test many times. For example, this one on head chamber as well. Next, then we and launch it for the first time. I haven't put the video for the launch of the first time. For satellite, the first objective was to simulate low Earth orbit for a cube satellite. Cube satellite means a cube means the size of satellite is 100 meters, 100 millimeter. So it means 0.1 meter. Okay? 0.1 meter. Đấy, vậy mà tập chung với mà tập anh đang là one cube sat and one. Sometimes we call one. Most of the time we call one unit of CubeSat. So here is just a simulation of low Earth orbit. So this represents a CubeSat and it orbits around the Earth. So and here is the equation and the flow chart or the block diagram to simulate the orbit of this satellite. Oh, actually this one for altitude determination. But a part of for altitude determination, we also the altitude means orientation. How I mean where the for example, if the camera, it has a camera, so where the camera pointing to, so it can be represented by quaternion or rotation matrix. So finding the orientation of the end effector or the payload is called altitude determination. So in order to find the altitude, we also need the orbit. So actually in this block diagram, there are a part of orbit simulation and also a part of altitude determination simulation. And also we simulate the detumbling using B dot control here. Detumbling means
for a satellite floating in orbit, if we don't have any controller, due to some small disturbance, could be it could be Earth's magnetic field or solar radiation or solar flare. It can cause it to rotate by itself. It rotates randomly. So detumbling means we use a control technique to make it stable in terms of, reduce the rotation. Do not allow it to rotate, but make it always pointing to the Earth, for example. Maybe not specific direction on the Earth, but at least the camera face to the Earth that can capture the image of the Earth, for example. But not really focus to like this point or this point or this point. Yeah, like not like that. That's called detumbling. And for the actuator, we can just use magnetometer for achieving the detumbling, meaning to say for achieving the camera always face to the Earth. But if we want to focus the camera to a specific location, for example here, or for example here, or if at the part of Cambodia where we want to point at the some part of Tonle Sap, okay, or some part to the city, or maybe some part to the forest. So we need a different actuator, okay. And now we are having a project to use a reaction wheel. To control the satellite to point to specific desired location. So reaction wheel, probably magnetometer is also used together, because sometimes if we only want the CubeSat to face to the Earth, you can only use magnetometer. We don't need to use this one. This one is probably more energy consumption need to be spent. Yeah, so there are more tasks to do. 6, 4, 5, 6, and even more. Maybe objective 7 is to launch. Okay. Launch the first satellite. I don't want to write satellite like this. Okay, that's all. So anyone has questions so far? មានទំនួលទេជាពិសេសបងប្អូនខាង Department Business គាត់សិស្សនៅ lab យើងពីច្រើនគាត់ join project ហើយអញ្ចឹងប្រហែលជាគាត់មិនសូវមានទំនួលទេ
បាទគ្រូអរគុណច្រើនគ្រូ process មួយចំនួនថ្មីដែរតែចំពោះកន្លែងខ្លះដូចជានៅក្នុងថ្នាក់ខ្ញុំក៏បានរៀនសូត្រធ្លាប់ធ្វើ assignment ឬក៏តាមតាក់ទងពីមុនអញ្ចឹង process ហ្នឹងខ្ញុំអាចយល់បានច្រើនដែរ
Okay, good.